Good. Hi, everyone. Thank you for the introduction. I first of all have to figure out how that thing is working. Yes, so good morning and thank you all for being here. I'm trying to show you a bit of our recent work on, as already introduced, on connectivity and how this is associated with the deposition pattern of tau that we see in aging and across different disease models. So, does that work? I should hit the green button, should I?
Yeah, it's green, but maybe try the mouse might be a little better.
Sure. Good point, thank you. So since this here is, as I guessed, a mostly non-clinical audience, I would like to briefly start with a short introduction on Alzheimer's disease, or short AD. It's by far the most common neurodegenerative disorder causing dementia in the elderly population, with the key symptom being a loss of episodic memory, meaning that storage of formation of new memories or retrieval of old memories vanishes as the disease progresses. And the prevalence is continuously increasing given that the population is getting older and older, or our life expectancy is getting older and older. The pathophysiological cascade of Alzheimer's disease is to date quite well described. So we believe that it starts with amyloid deposition in a form of extracellular plaques throughout basically the entire cortex, followed by the formation of neurofibrillary tangles made of tau. So this is an intracellular pathology, and very important here for the main message of my talk is that tau starts very locally circumscribed in the entorhinal cortex and then spreads gradually in a very stereotypic pattern throughout the cortex. So tau is really supposed to spread from neuron to neuron, and that in the end is associated with neuronal loss and memory dysfunction. So in previous years we were only able to assess tau pathology based on post-mortem staging, which was very well described by Heiko Brack and his wife. But the recent years of PET imaging have come up with tau tracers, here the first generation tau tracer, AV1451, which now allows a very nice staging of tau pathology in vivo, and we can here see on the left panel a normal aging subject who has no evidence of elevated amyloid pathology, where we see just restricted tau PET elevations in the inferior temporal lobe, whereas compared to in the middle panel, the Alzheimer's disease patients, they show really in the preclinical stage already a slight elevations also in the inferior temporal lobe, and then at the stage of full-blown dementia, basically the entire cortex is filled with tau. And what has been described more recently, which a very interesting finding from Korea, was that even subjects with small vessel disease, so who are amyloid negative, that they show also elevated tau PET signal, indicating that tau pathology may contribute to cognitive impairment in those subjects as well. So what is it that makes tau so special, and in particular its very stereotypic spreading pattern? It is assumed that tau may spread in a prion-like manner throughout connected neurons, which has been very elegantly shown here in that study, where Wu and colleagues co-cultured neurons in a tripartite chamber system, and they infected the first population with misfolded tau seeds, and after waiting for a while they were actually able to detect tau in the third population, indicating that the pathological tau seeds really traveled throughout the system via those neuronal connections. And even more importantly, they were able to show that the spread is facilitated by neuronal activity. So using optogenetics, they were able to stimulate, in a tau transgenic mouse model, to stimulate the hippocampus and show that the elevated activity within the stimulated region, here on the left hippocampus, was associated with an increased spread of pathological tau to the contralateral connected hippocampus. So basically that brings me down to the main idea of the current study, is that tau spreads transsynaptically in an activity-dependent manner, indicating that basically two neurons that share the same activity pattern, if we translate that to functional connectivity, should show covarying levels of tau, whereas two regions that are rather disconnected, who show a dissimilar activity pattern, should show dissimilar levels of tau. So, I already mentioned that we translated that concept to fMRI, basically to resting state fMRI connectivity, and we looked at that in 3 different study groups who all underwent resting state fMRI, tau PET imaging, and amyloid PET. And the images here are thresholded at a pathological tau PET uptake threshold of 1.2, where those guys who age normally in the absence of amyloid show only those restricted elevations of the tau PET signal within the inferior temporal lobe, whereas across the Alzheimer's disease spectrum you really see that gradual spread and increase of tau pathology, and in a very similar but slightly less elevated manner you find that same pattern in vascular cognitive impairment. So within each of those subjects we determined resting state fMRI connectivity using the very nice 400 RI parcellation by Alex Schäfer, yielding a representative connectivity matrix for each study group. And in the next step we assessed tau covariance, which was basically defined as, so we parcellated each individual's tau PET image into those 400 RIs, and then determined across subjects the correlation between ROIs, meaning that 2 regions who show a high correlation coefficient show covarying levels of tau. Basically that gave us those tau covariance matrices across the 3 different cohorts, and then for the main analysis we just did a simple association test, so whether functional connectivity predicted higher covariance in tau across those groups, and we found that to be the case as hypothesized across all these groups, where regions that showed higher connectivity showed more covarying levels of tau, and importantly that finding was independent of the distance between the regions, so that here it's really connectivity and not proximity that matters. So in the next step we then went ahead and asked, since tau is hypothesized to start very circumscribed in inferior temporal lobes, we asked whether connectivity of hotspot regions, so those regions who show very high tau in those groups, predict whether their connectivity pattern predicts tau in downstream connected regions. And indeed that was again the case across all 3 cohorts. Strongest association found as expected in AD, where the connectivity gradient of the tau hotspot predicted a gradient of tau throughout the cortex. And we repeated this analysis basically throughout the entire brain, where we plotted on the x-axis the tau PET uptake of a given brain region, and on the y-axis the, can I go back? Yeah, the beta coefficient that you see here in the upper panel. And what you see is that those regions with highest tau show they are more likely connected to other regions with high tau, whereas those regions with very low tau on the left bottom of the panels, preferentially the motor regions, are preferentially connected to other low tau regions. And to illustrate that point further, we rendered just the connectivity pattern in force-directed plots, where the proximity of nodes is determined by functional connectivity, and the size of nodes is determined by the tau PET uptake group average in that sample. And you can see that regions with similar tau levels cluster together, both on the high-end spectrum and on the low-end spectrum. So to sum that up, basically we believe that, or our findings show that tau covariance is associated with connectivity across both normal aging, AD, and vascular cognitive impairment. And very importantly, the connectivity pattern of those very early tau sites predicts a gradient of tau in the connected regions, whereas the opposite was found as expected for the regions with very low tau, so motor regions for instance. So in the end that leads us to conclude that tau spread may be facilitated by functional brain networks, which would be illustrated in that cartoon-like image, where tau pathology may start locally in circumscribed regions and then spread gradually throughout the network basically until the whole system is saturated. And we believe that maybe, since we found the same association across all those groups, that the local pressure driving tau out of those first hotspot regions might be dependent on the underlying pathological or non-pathological condition, where it's apparently highest in AD. And these findings were now purely cross-sectional, so a brief outlook of our more recent longitudinal study. We got the reviews back yesterday. They don't look too bad, to be fair. So here we looked at longitudinal tau change. So we computed the change in tau of a given region and looked at whether the change of tau in a given region predicts change of tau in downstream regions, and that just here illustrated as an example for the hotspot region, we found basically the same pattern, that regions which show a similar change in tau across time are also more likely to be connected to each other. And with that, I would like to conclude, to thank our collaborators, my lab, and in the end, you for your attention. Thank you.